All right, you ready?
Yeah.
All right, cool. So the question is how do we factor in the traction limits when you're doing the acceleration, right? So in our prior math, we said force of 16.68 kilonewtons is the maximum force that the powertrain can do based on all of our math, right? So, and that's actually at the start, during the constant torque, right? During the first half, constant torque, over here, this first half of the section right here, before the torque falls off, we can do 16.68 kilonewtons, okay? But that's assuming that we have infinite traction. So now we need to go over here and we take the weight of the vehicle times gravity, and you get your normal force of the entire vehicle. This right here is dividing by 2 because we're saying it's only a 2-wheel drive. And we're treating the axle as 1 wheel, even though there's technically 2. So half of the weight / half of the normal force is on where the axle that has the traction, that has the drive power, the torque, okay? So now we take, we're figuring out F traction. That was F normal force. Now we're figuring out our traction force. So we take the normal force times 0.7, and you get your, that's your force traction. That is the force at which anything more than that, and your wheels will slip out. Anything less than that, you're good. So this is the force that is allowed before slip out. And anything, anyway. So basically what's very interesting is your powertrain cannot actually use this whole 16 kilonewtons. You have to traction control it down to 7 in this situation. Now what does this force equal? This force equals, F equals ma, it equals an A of 3.44 meters per second squared, okay? And very easy math. We're going to use this speed is equal to acceleration times time, and that gives us a time of 7.796. But we made a big assumption there. We made an assumption that we are traction limited through the entire acceleration. But we know that we switch from torque limit to where the torque falls off. So as the torque is falling off, eventually we are going to find a point at which we're not traction limited, we're actually powertrain limited, okay? And that's what we figured out here. So this is the assumption that you're traction limited through the entire 0 to 60, 7.796 seconds. This is our quick math to figure out the point at which, what speed do you actually convert over to being no longer traction limited, but powertrain limited. So here's what we do. We take this F traction, we put it through this equation right here. We figure out the torque of the motor. Torque of the motor is 260 newton meters, which is really interesting once again because the motor can do 600 newton meters. So you have to limit it quite a bit. 260 newton meters is what you need to limit it down to in order to not spin out. So here is your torque curve for the motor. It's always flat at 600 newton meters, flat, then decreasing. It starts decreasing at the rated speed, which is 5,000 RPM. Sorry, that's a 5K. 5,000 RPM. We know that because rated speed, 5,000 RPM. Now, we made the assumption that the no-load speed is 10,000 RPM, and we are assuming that it linearly drops. So what is the speed where the motor hits 260 newton meters, right? So you look at this graph, you got 600 linear down to 0, between 5,000 and 10,000, okay? Use your high school algebra to figure out what speed your 260 newton meters is at, all right? And that is all this math. It's at 7,166 RPM is where you will start needing to, you won't be able to produce torque anymore that can slip out. So basically, 7,000 RPM, you no longer can spin your wheels out, okay? Which is actually pretty high, for the record. We converted this RPM to almost 30 meters per second. 30 meters per second is 66 miles per hour. So we know that 0 to 60, you are traction limited. 0 to 66, you are traction limited. And then after 66 miles an hour, you need to change your math because you're powertrain limited. So if I had this problem, which I wouldn't do this would be very mean, 0 to 80. What is your real world 0 to 80 miles an hour? Now you've got to figure this time out, and then you got to figure out your lowering. Your acceleration would actually lower. Your A would not be constant. So I won't make you do that. But okay, I think that's about it for the camera, you guys have any questions on that?
That makes sense.
So that's just the first half when it comes, or excuse me, that's the second half of this problem.